Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Today, inshallah, is the first lecture of a new session, session 12, in which we will discuss why the mean or the average of a list of values in a collection matters a lot in data science. In this specific lecture, we will cover or we will answer three questions. The first one, how can we interpret averages, and what is the difference between averages and medians? And then we'll talk about how we can quantify variability of a list of values in a collection. Let's start with averages. Of course, you are very familiar with averages since very long time, and we all know that the average is average of a list of values in a collection is the sum of these values over the number of these values. So if I have a collection of values like 2, 3, 3, 9, then the average is the sum of them over 4, which is in this case 4.25. Now let's talk about some facts about the value of an average. First, the average doesn't need to be a value in the collection. So as we saw, 4.25 doesn't belong to the collection of the values, but it is the average of them. The average doesn't need to be an integer, even if the data are integers, and that's very clear in this example also. The average is always somewhere between the minimum and the maximum values of the list, but not necessarily halfway in between. And this is also clear. The average has the same unit as the data. So if I'm averaging here temperatures, for example, in Celsius, then the average of them will be also at a temperature in Celsius. Now, here's a different concept. The average is a smoothing operator. So if we collect all the contributions or all the values in one bag and then split them evenly, split the contributions or the values evenly across the number of items in the bag or in the list, then this will be the value of the average. Okay? Because if I assign to each item in the list this value, all of them will be the same, and the sum of them will be the sum of the original values. There is another concept that we will discuss in the demo. So let's say that we have an array of 4 values here, 2, 3, 3, 9. That's the same one that we saw in the slide. Of course, the average is the sum of the values over the length of the values. Okay, so the average will be 4.25 as we saw. We can also use in NumPy 2 ways to compute the average function and the mean function. Okay. Now let's look at how we actually compute the average and try to rearrange the way that we do it. So the sum over the number is the addition of all the numbers, 2 plus 3 plus 3 plus 9 over 4. Now let me rearrange this in a different way. So I will distribute the division over each value here. So this will be 2 over 4 plus 3 over 4 plus 3 over 4 plus 9 over 4. Okay, so that's the same value. Now I see that the number 3 is repeated twice, so I will delete one of them and I will just multiply by 2 here. Okay, so that's again the same thing. Now let me make this more clear by saying 2 divided by 4 is 2 times 1 over 4, and 9 over 4 is also 9 times 1 over 4. Now if we look at this expression now, it looks like a weighted sum of the distinct values in the collection or in the array. So we have 3 distinct values in the array, which are 2 and 3 and 9, and it is now the mean is a weighted sum of these values. The weight of each distinct value is the proportion of appearance of that value in the array. So for example, 3 appeared twice in the array, so the proportion of it is 2 divided by 4, 2 out of 4. 2 appeared once, so the proportion is 1 over 4. 9 appeared once, so the proportion of 9 is 1 over 4. So the mean is the weighted sum of the distinct values, where the weight is the proportion of each distinct value. Or in other words, it depends on the distribution, because these weights are the proportions of the different values, so we can look at it as the distribution of the values in the array. So that means that the mean depends only on the distribution of the distinct values. If I know for each distinct value how many times it appeared in the array, or the proportion of its appearance in the array, then I can compute the mean. That also means that any array of values that have the same distribution, then the same, of course, distinct values, like the one that we are talking about here, will have the same mean. Let's see that in an example. Let's put the values, these values in a table. So this is one column table, and then look at the distribution of that table, of that array. So this is the distribution. 2 appeared once, 3 appeared twice, and 9 appeared once. Now let's try to compute the mean of another array in which we have 10 copies of each of the values in this current array. So I will use the function, the NumPy function full, to have 10 copies of each value in the array. So NumPy.full 10 and 2, that will generate or will create an array of 10 copies of 2. This one will create an array of 20 copies of 3. Why 20? Because I want to copy all the values in the original array 10 times. 3 appeared twice in the original array, so it will be 20 times, and 10 times of 9. So the new values array will have 10 copies of each of the values in the original array. Now I will put them in a table and draw the histogram. What do you expect to see as a histogram of this new array? It should be exactly the same like the original distribution. Okay, remember that the length here, okay, or the area here is the percentage. Okay, so it is by copying 10 times each value, we still have the same distribution. Okay, so having exactly the same histogram is not a surprise here. Now, what do you expect about the mean? As we said, the mean is a weighted sum of the distinct values where the weight is the proportion. Okay, so the distinct values here are the same in both arrays, and the proportions also are exactly the same. Okay, by copying, we didn't change the distribution, so the proportions are the same, so we expect that we will have exactly the same mean, although the number of values in the array now is multiplied by 10. So originally we had 4 values, here we have 40 values, but the mean is the same because the mean depends only on the distribution of the different values in the array. So if we compute now the average of the new values array, we will get the same number, which is 4.25. Let's get back to the slides and we'll continue talking about the concepts that we just discussed. Here's a discussion question for you. Looking at this histogram, create a data set that has this histogram. Okay, and you can do that with only values of integers. So if you look at this histogram, you will see that the value here repeated 2 times the times of this value, and this value is 3 times of this. So I can easily say that one possible array that has this histogram can have the value 1 once, the value 2 twice, the value 3 times, the value 4 2 times, and the value 5 once. So that's a data set or an array that will have this histogram. Now that's not the main question. The main question is what are its median and mean. If we calculate the median and mean in this case, we'll find that both are the same and both are at the value 3. Okay, looking at the histogram, it is very clear that the median and the mean will be 3. Okay, and we will see why in maybe a couple of slides. Now, so we started with this histogram. Now we have two histograms. This is the one that we saw in the previous slide, and here's the same histogram but with one modification. When we moved the value that was here 5, we moved it to the right a bit to be 10. Okay, now this is a different histogram. Now the first question is, are the medians of these two distributions the same or different? So the medians are the same or different. So what is the median value of a list of values? It is the halfway point, the point where above it the number of values that are larger than it is the same like the number of values that are below it. Okay, so the medians here will not change. It will be the same. Okay, although we took this value and instead of having 5, it will be 10, but still this value is the maximum, so the order of the values will not change a lot. The order will be the same, but the value itself will be different, but still this is the maximum value, but the halfway point is the same like here, so it will be 3, and also here will be 3. Okay, so the answer to this question is yes, they are the same. The second question, are the means the same or different? Okay, the means are the same or different. Now we can mathematically say, because the sum here will be larger than the sum here, then the mean here should be larger than here, which is of course true. But let me explain that in a different way. Let's imagine that these values are weights. Okay, so the bars here are weights, and I want to balance these weights over some point on this axis. Okay, so it's like I will put a balance point somewhere so that the two sides of the point will be balanced. So if I put the balance point somewhere here, then of course it will fall down the right side. If I put it somewhere here, it will fall down the left side, because the left side will be like heavier. Okay, so the mean actually is the point where it will the weights here will completely balance. Okay, so it's called the balance point, or it's also called the center of gravity. Okay, so the center of gravity is actually computed the same way like the mean, like the interpretation of weighted sum of the distinct values. So the center of gravity here, if you think about it, when this value was here, the center of gravity was somewhere in the middle. But as we push the value that were here, that were 5 on the left histogram, we pushed it away to the right. If you think about the balance point now, the balance point should go to the right or to the left to balance the two sides. Of course, it should go to the right. Okay, it should go to the right. So in this case, the mean will move away from the median. Remember, the median was 3 also, and the mean was 3 on the left histogram, but now we pushed the value 5 to the right, then the mean will be pushed to the right. In fact, the average here is 3.5, is about 3.5, which is a bit bigger than 3, that is the average in this case. If we push this value further to the right, we would expect, of course, the mean to be further also to the right. So let's compare now between the median and the mean. The mean is the balance point of the histogram, but the median is the halfway point of the data. So that half of the area of the histogram will be on either side of the median. So if you think about the areas of the bars in the histogram here, then the median point where the halfway point where the areas of the bars will be equal on both sides. So generally, if the distribution is symmetric about a value, then that value is both the average and the median, and that's why the mean and the median of this histogram are the same, because it is symmetric. The distribution of the histogram is perfectly symmetric. If the histogram is skewed, then the mean is pulled away from the median in the direction of the tail. Let's look at that in the previous example. So here, the distribution is skewed to the right, so there is a tail to the right, so the median will be far away from the, the mean will be far away from the median in the direction of the tail, which is in this case the right direction. Now, here is a discussion question for you to do. Looking at this histogram, this is the histogram of the height of NBA players in 2013. Tell me if the mean is bigger than the median or the opposite. So looking at the histogram, think about whether the histogram is symmetric or skewed, and if it's skewed, where's the tail? And if that's the case, then is the median bigger or the mean is bigger? Okay, we'll leave that to you. Now let's see how we can quantify the variability of the values in an array. The first idea is to compute the difference between the biggest value and the smallest value, or maximum and minimum. The problem with that is that it doesn't tell us anything about the values in between. It doesn't tell us much about the shape of the distribution of the values in the array. So many things can change within the values of the array, but still the range of between the maximum and the minimum, or the difference between the maximum and the minimum, will be the same. So this idea is not good. Another idea is to measure the variability around the mean or the average. But we need to figure out, of course, a way to do that. So let's see how we can do that over a demo. So let's start with the same array that we had in the previous demo, which is 2, 3, 3, 9, and put it again in a table and compute the average of it. So the average is 4.25 as we saw before. Now one idea is to compute the deviation of each value from the average. Now let's do that for all values and add a column in the array in the table that shows the deviation of each value from the average. So this is 2 minus 4.25 is minus 2.25, and so on for each value. Now you might be tempted to get the mean of these deviations as a quantity, or as an indication of how variable the values around the mean. Now if we look at the values here, we will see that the positive values will be cancelled out with the negative values. So once we get the sum of the deviations, we will get 0. So the sum or the mean will be 0. So to resolve this issue, we need to get rid of the sign here. And we have always two ways of getting rid of the sign. One with taking the absolute value, and the other by squaring. In this case, we will square, and because this is more common in the context of mean and variability. So we'll take the square. So we'll take the square of all deviations and add it as a column also to the table. So now we have the deviations and we have the squared deviation. Now we can get the mean of them. So that's now a sense of how variable they are, but each value is squared. We can get the mean of them, which is called the variance. So the variance here will be 7.68. And then since the unit here is squared, we need to get it back to the same unit of the values of the array. So we will take the square root. So taking the square root of the variance will give us what we know as the standard deviation, or ST. So the standard deviation is the square root of the variance. So that was just a demonstration of how the standard deviation is computed step by step. And of course, in NumPy package, we can use directly the function std or standard deviation to get the value of the standard deviation, which of course is the same like the one that we just computed. Getting back to the slides, and let's talk about the meaning of that. So the standard deviation is a measure of variability around the average. It tries to measure roughly how far the data are from their average. Formally, it is the root mean square of deviations from average. And if you look at this statement, this is exactly the way we compute the standard deviation, but in the reverse order. Okay, so we first measure or compute the average of the values, then we compute the deviations from this average. We take the square of it because we want to get rid of the sign. Then we get the mean of these squares, and we get the square root of that mean, so that we get back to the same unit of the data. So that's the standard deviation. And as we said, the standard deviation then, after getting the square root, will have the same unit as the data. Now, why we are using standard deviation to measure how variable the values are in the collection or in the array? There are two reasons for that. The first one is that no matter what the shape of the distribution of the data is, the bulk of the data are in the range average plus or minus a few standard deviations. So what is the meaning of this? That means that regardless of the distribution of the data, most of the data, that's the meaning of bulk, okay, most of the data will be in a range around the average. How can we quantify that range? It is bigger than the average with few standard deviations quantities, or smaller than the average with few standard deviation quantities. So it is the range, it is somehow most of the data is in the range of the average plus or minus a few standard deviations. Okay, we will talk about that in detail very soon. The second reason we will see it inshallah in the next lecture. So getting back to the first reason, so this is what we just mentioned is an informal statement of what is called Chebyshev's inequality. So Chebyshev's inequality informally says that no matter what the shape of the distribution of the data, the bulk or the most of the data are in the range average plus or minus a few standard deviations. Let's see formally how it is stated. No matter what the shape of the distribution, so regardless of the distribution of the data, the proportion of values, okay, in the range average plus or minus z standard deviations is at least 1 minus 1 over z squared. So that's the formal statement of Chebyshev's inequality. What does that mean? Let's see what exactly it means. So the proportion of the data, okay, within two standard deviations from the average will be at least 1 minus 1 over 4, which is 75%. Okay, so that means that at least 75% of the data in any distribution will be within 2 standard deviations from the average on both sides of the average. And at least 88.88% of the data will be within 3 standard deviations from the average. So minus 3 standard deviations plus 3 standard deviations. Okay, so let's say that standard deviation is 1. So that means that 88.88% of the data are located in the range the average minus 3 and the average plus 3. Also, if z is 4, then at least 93.75% of the data will be located or will be within 4 standard deviations far from the average, and so on if we want to try with multiple values of z. So that will give us a sense of how the data are distributed within any list of values. If we know the average and if we know the standard deviation, for sure we can say that at least 75% of the data are far from the average within 2 standard deviations. Okay, and 93.75% are within 4 standard deviations from the average, and so on. So that will give us a sense of how the data is distributed. So, and that's regardless of the distribution. No matter what the distribution looks like, these inequalities hold. Notice one very important thing is that we always say at least. Okay, we always say at least. What does that mean? It means that it can be, of course, more than that, but it cannot be less than that. Okay, so that's a lower bound. An upper bound can be much more than that, or the actual value can be much more than that, but at least will be that value for any distribution of values. Let's see a demo on that. We'll get back to the baby and mothers data set, and we will focus for now on the weight of mothers, or what we call maternal pregnancy weight. So here is the histogram of the weight of mothers in this data set. You will see that it is a bit skewed to the right. Okay, so there is a tail here to the right, a bit longer than the left side. Okay. Now let's compute the mean and standard deviation. So the mean and standard deviation for this is the following. So the mean is 128 pounds and the standard deviation is 20.72 pounds. Now let's see the proportion of the weights of the mother's weights within 3 standard deviations from the average. How can we do that? We will get the number of, we will focus on the rows where the weights are between the mean minus 3 standard deviation and the mean plus 3 standard deviations. Okay, so we'll get these rows, and to compute the proportion, we will divide by the total number of rows. So that will give us 0.986. So 98% or 98.6% of the weights in this data are within 3 standard deviations from the average. Now, what does Chebyshev inequality says? It says it should be 1 minus 1 over 3 square, which is 88%. Okay, so the inequality says at least 88.88% is within 3 standard deviations. The data here is consistent with the inequality, but actually it is much more than that. So it is 98.6%. But still the inequality, of course, holds, because the inequality says at least 88.88% will be within that range. Let's apply it on the other values in the data set. So we have multiple columns here. We have the weight, we have the age, we have the height, and so on. So let's apply that on all the columns in the data set. We will compute the proportions within 2, 3, 4, 5 standard deviations from the average, and compare it with the lower bound that Chebyshev told us. So let's run this. This will have a block of values for each column here. So for example, here is the weight, the one that we just looked at, but we looked at just one row here. So within 2 standard deviations, the data tell us that within 2 standard deviations we have about 95% of the data. Chebyshev bound is 75. The data told us that 100% of the data is within 4 standard deviations from the average. Chebyshev bound was 93.75. So you will always see that these numbers, okay, that are the actual numbers from the data, are at least or are greater than or equal to the numbers here. Okay, you look at the Chebyshев bounds, will be a lower bound on what we see actually in the data. By that, we end our lecture. Inshallah, next lecture we will bend on that, and we will see how the mean and the standard deviation are related to a bell-shaped distribution, or more specifically to the normal distribution. Thank you, and inshallah talk to you in the next lecture. Assalamu alaikum wa rahmatullahi wa barakatuh.